Hi, my name is Anna Liles, and I am a rising sophomore at UNC Chapel Hill pursuing a chemistry major and a Spanish for the health professions minor. I'm applying to be a peer mentor for Dr. Tiani's Chem 102 class this coming fall. And a fun fact about me is that I saw Africa this summer. I didn't actually go, I saw Morocco from the top of the rock of Gibraltar, which was very cool. I want to be a peer mentor because the peer mentors in my 101 and 102 classes were so helpful and such an important part to my success in those classes. And I think that as a peer mentor, I can really help those students in the 102 class really reach their full potential. I also think that teaching is such an important part of learning, and that as a mentor, I will really strengthen my foundation in the basic chemistry, and it will really help me as I continue to pursue my degree in chemistry. Thank you for watching, and I hope you enjoy the problem.
Consider the following titration curve produced by titrating 20 milliliters of an unknown weak acid with 1 molar of NaOH. What is the concentration of the original weak acid in molarity? Molarity is a measurement of concentration in moles over liters. Since we know the volume of the original weak acid, all we have to measure are the moles. We can do that by looking at the equivalence point on the graph, which is where the slope of the graph reaches about 0. This is also the point at which the molar amount in the added base is equal to the molar amount in the weak acid. That occurs at about 46 milliliters in our titration curve. Now we take the concentration of the NaOH solution, which is 1 mole over a liter, multiply that by the volume, 46 milliliters, and convert the milliliters to liters, and we find the amount of moles in the NaOH solution at the equivalence point. .046 moles. That is the same amount of moles that are in the weak acid solution, so all we have to do is divide that by the volume, and we get the molarity, which is about 2.3 molar. Our second question is, what is the Ka of this acid? For this question, we're going to use the Henderson-Hasselbalch equation, which is pH equals pKa plus the log of the conjugate base over the conjugate of the weak acid. This is an equation we can use when dealing with buffers. And when we look at our titration curve, which will come up in a moment, we know that all the space in between the equivalence point in the beginning of the titration is the buffer region. Specifically, we're going to look at the 23 milliliters mark, which is the half equivalence point. At this point, the concentration of the weak acid is equal to the concentration of the conjugate base. So when we look back at our Henderson-Hasselbalch equation, we see that that cancels out to 1, and so the entire log expression is equal to 0 and goes away. And the pH equals the pKa at the half equivalence point. So we're going to go back and look at the pH at the half equivalence point, which is about 6.00. So pH equals 6 equals the pKa. Now it's an easy conversion from the pKa to the Ka. Negative log of Ka equals pKa, or Ka equals 10 to the negative pKa. So the Ka equals 10 to the negative 6. Or, when we correct for sig figs, 1.00 times 10 to the negative 6 is our Ka. And that's our solution.